In section 4.6 of the textbook, your author provides a procedure to do what's known as applied optimization. The idea in an applied optimization problem is that we take a real-life scenario and then we either find a maximum or a minimum value, finding the optimal solution. So I want to start with an example, and then at the end of the video I'll put up the author's procedure for providing a solution to an applied optimization problem. But the real idea is that we're going to take all the information we've learned so far in chapter 4 and apply it to application problems. So let's say I have an open top box that I want to make by cutting squares off of a note card. So an open top box is to be constructed by cutting congruent squares from the corners of a 5-inch by 3-inch note card and folding up the sides. What side length should the squares cut from the note card be to maximize the volume? So I take my note card, and off all 4 corners, I simply cut a square off. And then that would give me a shape that looked like this, and then I get to fold up the sides, right? And that forms my open top box, right? I need to use a piece of tape, and most times if you see this question stated, or if it was to actually come up in a scenario, you would probably be using a piece of steel or something that you could weld on the sides and form an open top box. All right, so at least I understand how to form the box, right? I cut squares off the corners, I fold up the sides, and now the question is, what length of square? What's the side length of the square that will make the box have the highest volume, right? Maximize the volume. Well, it's not this one. I just kind of cut squares off how I felt like on this one. They probably weren't even really squares, but we'll pretend. And so what I'm thinking is that I started off with a 3-inch by 5-inch note card. I cut corners off of it. And then I folded up the sides that remain to get a box. And I'm asked to maximize the volume. So I think I need a function for volume, because if I had a function on volume, then I could do some calculus to find minimums and maximums. So what should the variable x be? Well, the thing I'm controlling, the thing I'm wondering about are the side lengths of the squares. So let's call that x. And so x is the size of square, the length of square I'm cutting off the corner. And what I want to do now is use that to label the sides over here. Because if I can tell you the length, the width, and the height of the box, then we can write down a formula for volume. So if I look at the side that used to be 5 inches long, when I cut off the squares, I raised up the sides, and instead of being 5 inches long, it was shorter. Well, I called this amount x, and I called that amount x. That's what I cut off, and so this side here is 5 minus 2x inches long. Using a similar amount of reasoning, if I look at this side that used to be 3 inches long, I cut off x on that side, I cut off x on that side, and this side would be 3 minus 2x long. And thinking about the way I formed the box, this is x long, and I fold that up to become the height of the box. And so the height of the box is simply x units long. Now I have a length, a width, and a height, and I can tell you that the volume is x times 5 minus 2x times 3 minus 2x. All right, so I have a function for volume. What's even better is this is a continuous function for volume because it's a polynomial. So I'm thinking we can use the extreme value theorem to find out the absolute minimum and absolute maximum, but to use the extreme value theorem, I need a finite closed interval. So I need to tell you the largest thing I think x can be and the smallest thing I think x can be. If I look at my note card and I think about the 3-inch side, right, I cut off some amount x from both sides, giving me that 3 minus 2x. Well, if I just think about it, if I let x be 1.5, I would cut all the way to the middle on both sides, and I wouldn't even be able to form a box. So I think x cannot be more than 1.5, 3 over 2. X definitely needs to be bigger than 0, because if it was 0, I wouldn't cut anything off, and I'd just get this note card, which isn't really a box, but we could think of it as kind of a flat box, not very useful. So now I have a continuous function over a finite closed interval. I know a continuous function has to have both an absolute minimum and an absolute maximum on this interval, and that maximum has to occur at one of the endpoints or at a critical point. So what we need to do now is take a derivative of v and evaluate v at any critical points we find and at both endpoints. So our volume function was x times 5 minus 2x times 3 minus 2x. X had to be between 0 and 3 over 2. So let's multiply this together, and then we'll take a derivative. Let's see, 5 times 3, 15. Minus 10x minus 6x gives me a minus 16x in the middle plus 4x squared. And now I need to distribute that x through. All right, so now I have a function for volume that is easily differentiated. So now I need to find any critical points, which is where this derivative is either equal to 0 or undefined. Well, this is a parabolic function, a quadratic function, so the derivative exists everywhere. So all I need to do is set it equal to 0. All right, so I could factor it, I could use the quadratic formula. I'm going to use the quadratic formula. All right, the opposite of b plus or minus square root of b squared. 32 squared is 1024. Minus 4 times a times c. 4 times 12 times 15 is 720. All over 2a. All right, so let's see. 1024 minus 720. Under the radical, I would have a 304. And I could simplify this and find an exact answer, but I think I want a decimal approximation. So I'm going to use my TI-83 to get a decimal approximation just off screen. All right, with the plus in the formula, I find out that x would be about 2.06 inches. I know I'll have to throw that one away right away because that's over that 1.5. I can't cut over 2 inches off of both sides of the 3-inch side. Or x would be about, and let's replace that plus with a minus, about 0.61 inches if we wanted to round to that first decimal place. Okay, now, we have an answer, but we're not sure it's the place that maximizes volume yet. We've just found a critical point. And this is a place in the problem where students will make a critical error and stop and just claim that that's the maximum. We have to do some amount of calculus to confirm that a maximum occurs there. And at this point, you could use the extreme value theorem, which is what I'm going to do in this problem. You could also use the first derivative test. You could check to make sure the first derivative changes sign from a positive to a minus, saying that this is a maximum value. You could also use the second derivative test for local extreme values, but you have to do some amount of calculus to see if this is a max or a min. In this open top box problem, this is very likely a maximum value, but we don't want to just guess on it. And the other thing we want to be careful about, if this was a problem about cost and the cost function had both a maximum and a minimum, and you find the wrong one, that would be very bad. So the extreme value theorem says that my absolute maximum and minimum occur at either an endpoint or a critical value. So what I need to do now is evaluate my function at these three values, the critical point that's in my interval and both endpoints. The largest thing in this table will be the absolute maximum value, and the smallest thing in this table will be the absolute minimum value. Well, my volume function is sitting right up here, and if I plug 0 in for x, I will definitely get a 0 out. Hopping down here, if I plug 3/2 into this part, that part will become a 0. 0 times anything is 0, and I will get a 0 out. And so all I need to do now is plug 0.61 in to the volume function. So 0.61 times 5 minus 2 times 0.61 times 3 minus 2 times 0.61. And I get about 4.104. Well, clearly the largest thing in the table is 4.104 and the smallest thing in the table are 0. So the absolute maximum between 0 and 3/2 has to be 4.104. The side length the side length x that needs to be cut off to maximize volume is about 0.61 inches. And that's what I was asked to find. If I was asked to state what the volume would be, well, I'd have to say it's about 4.1 cubic inches. I wasn't asked for that. Here at the end of this problem, before we look at the procedure in the textbook, I marked a note card with a side length, the squares that I traced out on there of length about 0.61 inches. I'll be honest, I didn't have a very fine measuring device to use to measure it, so this is actually 5/8 of an inch, so a little bit larger. But I thought we'd take a look at what the maximized box, or approximately maximized box, would look like. If we were in a classroom together, I would make a student cut these squares off so that I didn't have to do it myself. This is one of the limitations from teaching at home. So. All right. Fold up the sides and form the open top box of approximately maximum volume. And there we have it. It would be a box that was kind of shallow, but apparently this has the maximum volume. Okay, so here's the procedure we just used. On page 264, you will find it. Solving applied optimization problem. Step 1, read the problem. That's kind of a funny thing. Of course, we're going to read the problem. What's the important part is to understand the problem. In a real application problem, sometimes the problem's not even written down. Someone tells you about it or you come across it, and the key is to understand the problem. Draw a picture in step 2. Label any part of the picture that might be important to the problem. Introduce variables. In our problem, no one told us to call the side length we were cutting off x. In fact, a side length I would typically call s instead of x, and you can make up the variables. But when you assign something a name, you need to let your reader know that. And so we introduce variables and we write those things down. Write an equation for the unknown quantity. This is where we found the volume equation. If you can, express the unknown as a function of a single variable or in 2 equations and 2 unknowns. This may require considerable manipulation. Sometimes we might have to work hard to find the formula or formulas we are going to use. And finally, in step 5 is where we do the calculus. We have to test the critical points. We're going to take a derivative. We might test endpoints in the domain. We can use what we know about the shape of a graph. We can use the first and second derivative tests to identify and classify the critical points. In step 5, that's where we actually use the information that we've studied here in chapter 4. After this video, you'll find more examples.